An electrical installation app is a powerful engineering tool that simplifies the process of sizing electrical components, eliminating the need for traditional pen and paper methods, manual calculations, and book searches to achieve optimal results. Visit the website provided in link below this video. Scroll to bottom of Webpage, then download the app in your device. After the app being downloaded, simply open the app, scroll through the home page, and drag the element you need to size. Let's start on breaker and cable sizing. This page is designed to assist in sizing cables and breakers, according to the IEE Wiring Regulations Guidebook, using formulas and tables from BS 7671 Appendix 4. Let's start an example. Fill the power in kilowatt as described here in this dialog, say 250 kilowatt. Voltage, say 400 volts 3-phase power source. Length of the cable from the power source to targeted load, 250 meters. As per BS 7671, the maximum allowable voltage drop at the load point should not exceed 3% for lighting and 5% for other uses. Let's say your load is power, and desired to be 3.7%. Designed power factor is 0.9. Select the power type 3-phase, AC. Here also you can select one of the standard cable types, either PVC with 70-degree operating temperature or XLPE rubber EPR with 90-degree operating temperature. Clicking this icon will take you to a list of installation methods. This list is from IEE Wiring Regulation BS 7671 Appendix 4, Table 4A2. Now choose one of the installation method applicable to your load. Scroll up and down, or you can simply type one in the search bar on top of this page. Here below are a few parameters that need to be confirmed, as they lead to derating factors that significantly impact the calculation of the tabulated current capacity. The first parameter in the selected installation method is the type of protection being used. If it is a fuse, the derating factor is 0.653. If it is a circuit breaker, the factor is 0.9. as per this reference clause obtained from Appendix 4. Next, determine whether the load requires overload protection. If it does, the calculation formula differs from the one used when overload protection is not required, as shown. Now, select the ambient temperature for the cable installation. The derating factor is negligible, equal to 1, when the ambient temperature is 20 degrees Celsius for underground installations and 30 degrees Celsius for above-ground installations. Other derating factors are listed in Appendix 4, Table 4B1 for above-ground installations and Table 4B2 for underground installations. Scroll to select the factor applicable to the installed cable. If thermal insulation is applied along the cable run, the derating factor will vary depending on the length of the insulation. The applicable factors can be found in the reference table which extracted from Chapter 52 of the same guidebook. Example, select insulation length 100 mm. Hence the factor is 0.78 as you see. Since our selected installation method is in-ground cabling, determining the laying depth is essential to identify the derating factor. The factor also varies slightly depending on whether the cable is laid directly in the ground or in a duct. Refer to this table in Appendix 4. Now, select 1.25 meters laying depth. As an example, soil thermal resistivity also contributes significantly as a derating factor for underground installations. In Table 4B3 of Appendix 4, the factors for cables buried directly are different from those for cables laid in ducts. For example, choose 1.5 value. Therefore, the derating factor is 1.1. The last parameter on this page is the grouping factor. This applies when a selected cable is installed within a group of multiple cables. The spacing between them creates a derating factor that significantly affects current capacity calculation. Therefore, when there is only a single circuit, the derating factor is negligible, with a value of 1. Keep in mind that we have selected the underground installation method, and the cable is laid in a duct. Refer to Table 4C3 in Appendix 4. The derating factors vary when 2 or more cables are laid in touching or spaced ducts, and these values also change based on different spacing and the number of adjacent ducts, as shown here. Now, select a spacing of 0.5 meters, with a total of 5 cables laid, including this one. Thus the factor is 0.85. Now, hit Calculate button to see the result. As you can see on this result page, The required circuit breaker and cable sizes are provided directly. The cable results indicate 3 runs for each phase and neutral conductor, along with the earth cable size. Additionally, the voltage drop has been considered and is shown on this calculation page. To understand how these values have been calculated and sized, the formulas and guidelines for the calculation steps are outlined below. We will go through each step in detail for your convenience. The second part on this page lists the parameters selected on the previous page. In the calculation section, the design current IB is calculated using the three-phase equation. It is equal to the power in watts divided by the square root of 3, multiplied by the voltage and the power factor. Apply the given parameters to this formula. The supplied power is 250,000 watts, divided by the square root of 3, multiplied by 400 volts and a power factor of 0.9. Thus, the design current is calculated to be 400.94 amperes. The tabulated current in Appendix 4 must be greater than or equal to the designed current divided by the product of the derating factors. The tabulated current capacity, in amperes, is detailed for each cross-sectional area of a copper conductor in Appendix 4, based on the type of cables used, the operating temperature, and the installation method applied to the load. Remember, the derating factors were determined on the previous page based on the selections made, and are also listed at the bottom of this page. Applying the designed current and derating factors determines that the tabulated current must be greater than or equal to 636.3 amperes. Therefore, the standard breaker size that is equal to or greater than this value is 800 amperes. Given that the installation method applied to the load is D, underground installation in a duct, and the selected copper conductor has a 90 degrees Celsius operating temperature with XLPE/EPR insulation, and for three-phase load, you should refer to Table 4E4A in Appendix 4. Search for a current value greater than or equal to 800 amperes under D installation method column. Based on the table, 281 amperes times 3 gives the appropriate current capacity, requiring 3 runs of a 185 square millimeters conductor cross-sectional area. Additionally, the result page provides details of what was explained. This reference directly indicates where the current capacity value was obtained, from the specific table in Appendix 4, the column corresponding to the installation method and type of load, and the row where the identified current value determines the cable size. Current capacity alone is not sufficient to determine the cable size. The voltage drop must also be evaluated to ensure it is within the desired limit. If the voltage drop is less than or equal to the allowable value, the cable size is acceptable. However, if it exceeds the limit, a larger cable size is required. The voltage drop is calculated as the product of the full load current, the cable length, and the voltage drop, VD, value in millivolts per ampere per meter, then divide the result by the supply voltage to express the voltage drop in percentage. In this example, the VD value can be obtained from Table 4E4B in Appendix 4, referring to column 4 for three-phase load and the row corresponding to a 185 square millimeters cable size. Since the current is distributed equally among 3 cable runs, divide the table value by 3. This gives approximately 0.087 millivolts/A/M. Substitute this value into the formula. The calculated voltage drop in this case is approximately 3.45%. Since the resulting value is less than the desired value of 3.7%, the selected cable size based on the current capacity is acceptable. Now, by pressing this icon you can get the detailed result in PDF. You can share this file with others or save it in your device directory. Also, you can access a few extracted page of Appendix 4. Next, quantify the number of earth rods and their measurements of an earthing system. This calculation page is based on BS 7430, 2011 Code of Practice for Protective Earthing of Electrical Installations. To determine the quantity and depth of earth rods required for an earthing system, the Wenner method, 4-probe method, is used to measure the soil mass resistance to fault currents. Begin testing by selecting a flat area near the earth termination point. Using a 4-probe tester, Place the device at the center, ensuring the 4 probes are evenly spaced at equal intervals, A, and inserted to a depth of 200 mm each. Apply the spaces of 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.51 and 0.5 meters. Let's consider this example. Data was collected at one of the sites by measuring the apparent soil resistance using a Wenner measuring device. The applied spacings, A, are listed in the first column, and the corresponding measured resistance values, R, are shown in the second column. The soil resistivity ρ is calculated as the product of 2 pi, the spacing, A, and the measured resistance value, R. This formula, known as the Wenner formula, is derived from clause 9.4 of the BS 7430 guidebook. Now, let's enter these data into this page. Since the total number of measured values is 12, scroll down to 12. Enter the first spacing, A, which is 10 meters, and the measured soil resistance value, R, of 0.01 ohms. The soil resistivity ρ is instantly calculated and displayed based on the aforementioned Wenner formula, in ohm meters. Next, enter the second set of values, and continue this process until all the data has been entered. Clicking this icon will take you to multiple choices of earthing systems. 4 options for earthing system methods are provided based on the clauses in the BS 7430 guidebook. Clause 953 for single rod earthing, 954 for parallel connection of aligned multiple rods, 9581 for 3 rods installed in an equilateral triangle, and 956 for mesh earthing installation. Let's choose the third one as an example. We'll aim for a target resistance of 1 ohm. The earth rods are available in metric units with diameters of 16 and 20 mm. Select the 20 mm diameter. The spacing between the rods say 5 meters. Now hit Calculate button. This table lists the data that have been entered along with the corresponding soil resistivity values. At the bottom of the table, the average soil resistivity of the 12 entries is displayed. The chart below the table represents the graph of soil resistivity values in blue, with their average shown as a yellow line. Here is the direct result for the required length of the earth electrode rod, which is 1.1 meters, to achieve the desired earth resistance value of 1 ohm or less. The calculated earth resistance value, based on this length, is 0.973 ohms and is derived using the average soil resistivity, ρ. This also represents the selected earthing system method of 3 rods installed in an equilateral triangle. To understand how the rod electrode length is determined, here is the formula for the configuration of 3 rods installed in an equilateral triangle, as outlined in section 9.5.8.1 of the guidebook. R represents the targeted earth resistance value, which is determined to be less than or equal to 1 ohm. The formula calculates R as 1/3 of the average soil resistivity, ρ, divided by 2 pi times the length of the earth rod to be determined, multiplied by the natural logarithm of 8 times the ratio of the rod length to its diameter, minus 1, plus 2 times the ratio of the rod length to the spacing between the 3 rods. To get the same in PDF, hit this icon. You can also have a look at a few extracted pages from the guidebook related to what is included in this calculation page, by clicking this icon. Next, to size the capacitor bank, click on this widget. Capacitor or capacitor bank is used to correct the power factor in low power factor systems caused by inductive loads such as motors, transformers, and large HVAC systems. To size the capacitor reactive power, adjust the desired power factor to a value greater than the actual power factor, for example, 91%. Then, set the actual power factor, say 81%. Enter the active power, real power in kilowatt, say 100. Voltage, say 400 volt, and utility frequency, 50 Hz. Hit Calculate button. The result value, in kVAR and microfarads is instantly displayed. Let's examine the power triangle to understand the components of the power vectors. Here is a graph showing two power triangles. The first represents the system before power factor correction, and the second represents the system after correction. The capacitive reactive power is the counterpart of the inductive reactive power, represented by Q1 and Q2. Theta 1 is the phase displacement angle before power factor correction, which is equal to cosine inverse of actual power factor 0.81. Theta 2 is the phase displacement angle after power factor correction, which is equal to cos inverse of desired power factor, 0.91. Q1 is the stored energy reflected in the source like magnetic fields around inductive components. Lagging reactive power, before correction, in other words, uncorrected reactive power which does not do any useful work, expressed in var or kilovar, which is equal to tan theta 1 multiplied by the power P. Whereas Q2, the stored energy reflected in the source like magnetic fields around inductive components, lagging reactive power, after correction, in other words, left uncorrected reactive power, which is equal to tan theta 2 multiplied by the power P. QC is the calculated reactive power of the capacitor bank, stored in electric fields, leading reactive power, within capacitance components. It is required to correct the power factor to near unity, or, as in this example, to the desired reactive power Q2. Thus, QC is the result of Q1 minus Q2. Here are the definitions of all the elements of the power triangle. To get this information in PDF, click this icon. To size the electrical metal trunk, hit this widget. This calculation page is based on BS 7176, Appendix 5, Tables 5E and 5F. Table 5E provides the capacity factors for standard cable or wire cross-sections based on their insulation type, whether thermoplastic PVC or thermosetting XLPE/EPR. Table 5F specifies the capacity factors for various metal trunking sizes. Let's start with this example. Here, you can select one of the standard cable sizes, the cable type, the number of circuits of the same size being installed, and the number of wires per circuit. Let's keep the default selections for the cable size and cable type, 1.5 square millimeters for the first wire size and thermoplastic for the insulation type. Adjust the number of circuits to 3, with 3 wires per circuit. You can add one more run by clicking this icon. You can add up to a total of 12 runs. This is a random example of selecting the next cable size for each subsequent widget, and so on. After completing the entries for 8 runs, click the Calculate button to view the result. This result page instantly displays the required metal trunk size to accommodate the specified group of circuits. To understand how it is sized, refer to the table below. It details the selected cable's cross-sectional area, cable type, number of circuits with the same size and type, quantity of wires per circuit, and the capacity factor of the cable. The capacity factor is obtained from Table 5E in Appendix 5 of the BS 7671 Guidebook. Total capacity is calculated by multiplying the number of circuits, the quantity of wires per circuit, and the cable's capacity factor. The summation of the total capacity factors above equals 3011.6. Therefore, from Table 5F in Appendix 5 of the Guidebook, find a trunk size with a capacity factor equal to or greater than this value. As a result, a 150 x 50 trunk with a capacity factor of 3091 is the suitable size, ensuring that the selected circuits can be accommodated while keeping the total wire space factor within 45% of the trunk's net size. These charts represent the occupied spaces. The top chart shows the occupied space per selected wire size per run in terms of total space factor, while the bottom chart represents the total occupied space relative to the trunk's capacity factor. To get this information in PDF, click this icon. This icon allows access to the relevant pages in the guidebook. Last, press this widget to size the electrical wires conduit. This calculation page is based on BS 7176, Appendix 5, Tables 5A, 5B, 5C, and 5D. Table 5A provides standard wire capacity factors for conduits that are 3 meters or shorter. Table 5B details conduit capacity factors based on diameter, in millimeters, for short, straight conduits up to 3 meters. Table 5C presents wire capacity factors for conduits longer than 3 meters, incorporating bends. Table 5D lists conduit capacity factors for both straight runs without bends and straight runs with bends. Consider this example. Select an 8-meter long electrical conduit with 2 bends along the run. Similar to metal trunk sizing, if multiple circuits with different wire sizes are drawn in the same conduit, select the wire size for each run and the number of wires per circuit. Now, as in trunk sizing, you can add up to 12 runs. In this example, 7 circuit runs are being added. This result page instantly displays the required wires conduit size to accommodate the specified group of circuits. To understand how it is sized, refer to the table below. Total capacity is calculated by multiplying the number of wires per circuit and the capacity factor of the wire. The total capacity factor from the summation above equals 1054. Therefore, refer to Table 5D in Appendix 5 of the guidebook to find a conduit size with a capacity factor equal to or greater than this value. Considering an 8-meter conduit length with 2 bends along the run, the suitable size is a 50-millimeter conduit with a capacity factor of 529, capacity factor of the 32 millimeters conduit, multiplied by 2.6, resulting in 1375.4. These charts represent the occupied spaces. The top chart shows the occupied space per selected wire size per run in terms of total space factor, while the bottom chart represents the total occupied space relative to the conduit's capacity factor. To get this information in PDF, click this icon. This icon allows access to the relevant pages in the guidebook. This is the end of the tutorial. Now, you can enjoy this app by going to the subscription page. On this page, 4 subscription options are available: 3 months, 6 months, 1 year, and lifetime. A 3-day free trial is included with any of these options. Finally, don't hesitate to message me. Your opinion matters.